Real exam questions. This is question 27 about beam design. The optimal effective depth of rectangular single reinforced cross-section in C30-37 is given by D is equal to 2.31 square root of the bending moment divided by BFCD. What is the optimal effective depth of a rectangular single reinforced cross-section with a concrete quality of C90 105? What does optimal effective depth means? Sketch the corresponding strain diagram, sketch the corresponding stresses, determine the rotational equilibrium around tensile reinforcement, express D as a function of B and MD, and compare both formulas with an example. What conclusion can you draw from this? Let's first start with the definition of optimum depth. Of what do you mean by optimum depth? The optimum depth of a reinforced beam, the optimum, is the effective depth at a given bending moment in ultimate limit state persistent, at which the limit value of strain in the concrete and steel are reached. So optimum means full exploitation of the ultimate resistance and is therefore not necessarily the most economical depth. When we look at the concrete tables or the different parameters of the concrete in function of their concrete grade, then you will see that for C90 105 that the strain epsilon C2 and epsilon CU2 are the same. So this means that there is only a parabolic part of the stress strain curve of the concrete. The 1.4 is the exponential coefficient of the parabola relationship. So epsilon CU2 is 2.6, epsilon C2 is also 2.6, epsilon UD, the maximum strain in the steel, is 10 per mil, and the coefficient N is 1.4. So now we look at the strain diagram where the use of materials is maximized. So that means epsilon C is equal to epsilon CU2, which is 2.6, and epsilon S is equal to epsilon UD, which is 10 per mil. From the strain, we transform it into the stresses, and you see this is only one part of the parabolic relationship. We can now calculate the total force, compressive force by the concrete, and there is a bending moment M on the section. And this means that you have the filling coefficient times the width or times the position of the neutral axis times B, which is the width of the section of the concrete, and times the stress FCD. But that means that you have a rectangle like this. So that's why we need the filling coefficient in front of it. We can do that by just integrating the curve, and that means from 0 to x, you integrate BFCD, and then the relationship of strain and stress of the concrete with the coefficient 1.4. And you see that for S equals to x, then you got here 0. So 0x, so for S equals to 6, S starts from the top downwards. And when you calculate this integral, you find this expression. Now, those must be equal to each other, so you can see that the filling coefficient is 7/12. Now we calculate the rotational equilibrium to find out what is delta G. So it's, of course, X minus delta G, X multiplied by the total component, compressive component in the concrete. So you have, this is the bending moment around the neutral axis, only from the concrete. And then you will again integrate it, make the integration of it, and then you will see that if you work this out, that delta G is equal to 6/17. Now, let's consider the whole picture. We got FCD is equal to 0.85 times 90 divided by 1.5. This is FCK, and this is the material coefficient, and this is alpha CC, and FCD is the design value of the compressive stress, and it's 51. X, it can easily be calculated using the similar triangles. So X is always D multiplied by epsilon CO2, which in our case is 2.6, divided by the sum of those two, which is 10 plus 2.6. So X is D times 13/63. We know that delta G was 6/17. So the bending moment, the resisting bending moment is then C FCD dx times d min delta G x. So it's the equilibrium around the tension reinforcement. You can fill in the different parameters, and we got an expression in function of d squared. That was so. Now we can, from this expression, we just turn around the formula and find d, which is then equal to d optimum, as this expression. So for C3037, the d optimum was equal to 2.31 times this square root, or if you fill in, of course, dFCD, this value you know, because it's C3037, you find this expression. It's 0.56 times the square root of the bending moment divided by the width of the section. For C9 V1 over 105, we have found or calculated this relationship, and you see that on those two numbers, that the optimum depth of a beam in C9 V105 is 25% smaller than a beam in C3037. So if you do not have enough height, you can try to use a higher concrete quality.